In this video, we're going to show the key property behind RSA encryption. Show that's actually true. That is, pick any two primes p, q, and let n equal p times q for any e relatively prime to p minus 1, q minus 1. First, the mapping from x to x to the power of e mod n is a bijection. That just means it's invertible. I have some way of undoing this thing. And the inverse mapping, the way that I undo it, is easy to find. Let D be the inverse of E modulo P minus 1 Q minus 1. Then for all x between 0 and n minus 1, we're basically saying that x to the power of E to the power of D is equivalent to x mod n. So it's saying that if I take my encrypted message, raise it to the power of D mod n, then I'll get back to my original. To prove this, I'm going to need to know two things. I'm going to need to know Fermat's little theorem, which we've seen in previous videos. And I'm also going to need to know the fact that if A is a multiple of primes P and Q, then A is a multiple of P times Q. It does matter that these are primes. For example, 18 is a multiple of both 6 and 9, but certainly 54 does not divide 18. 6 and 9 have some shared factors, which makes this thing not work as well. The fact that these are prime means that they share no factors, and this thing is true. So, in order to prove this, we actually only need to prove the second part. And what we're essentially trying to prove, we want to show that x to the power of ed, this is just another way of simplifying this using the exponent or properties, is equivalent to x mod n, or that x to the power of ed is equivalent to, x to the power of ed minus x is equivalent to 0 mod n. And the reason we might want to write it this way is because this is another way of saying that this is exactly equivalent to saying that x to the power of ed minus x is a multiple of n. Okay. So here is where we might kind of pull up our first trick was subtracting x from both sides to get it expressed in this multiple language. The next trick that we're going to do is instead we want to show that x to the power of ed minus x is a multiple of both p and q. If it is, then it's also a multiple of pq, which equals n. And that's by our second property here. Okay, so that's kind of our goal. We've taken one question and then turned it into a totally different question, which will somehow show the same thing. Now, we can't start by assuming that this is true, but what we can do is we can ask, what is x to the power of ed minus x mod p? If we can show that it is equivalent to 0 mod p, then we're done, because that shows that it's a multiple of p, and we're good. Well, since ed is equivalent to 1 mod p minus 1 q minus 1, what that means is that then ed, it's going to equal 1 plus some constant times p minus 1, q minus 1. And if you look back at our definition of division that we used for the division algorithm, you should see something like this show up. This is our remainder, this is our dividend, and this would be our quotient, and we're saying, so it all works out. I think this is the dividend, that's the divisor. It's been a while since I was in middle school. I don't remember those words. That's okay. Anyhow, so that's essentially what this is saying, that ed is equivalent to 1 mod p minus 1 q minus 1. So let's just replace that. Substitute this in. That tells me that x to the power, now I'm looking at what is x to the power of 1 plus k times p minus 1 q minus 1 minus x mod p. And now I'm going to do some tricks. One trick I'm going to do is I have some addition here. Due to my exponent properties, I can rewrite this as x times x to the power of k, p minus 1, q minus 1, minus x mod p. And then the next trick that I'm going to use is I'm going to kind of do some grouping here. I'm going to write this as x to the p minus 1. And then I'm going to raise all of that to the power of k times q minus 1 minus x mod p. X is between 0 and n minus 1. Actually, let's take another step back, because we're not actually looking at n here. We're now looking mod p. So we can just assume, for the sake of argument, that x is less than p, because we're looking in the case of mod p. So we can consider everything to be less than p, between 0 and p minus 1. And thanks to Fermat's little theorem, that tells me that this x to the p minus 1 is just going to be 1, or equivalent to 1 mod p. And maybe now you can see where we're going with this, because 1 to the power of anything is just still going to be 1. So this is going to be x minus x mod p, which is equivalent to 0 mod p. So this shows me that x to the power of ed is equivalent, or minus x, is a multiple of p. Because I showed that it's equivalent to 0 mod p. Let me get myself a little bit more room here. By the exact same argument, x to the power of ed minus x is a multiple of q. So x to the power of ed minus x is also a multiple, of pq, which is just n. So going kind of backwards, we have that x to the power of ed minus x is equivalent to 0 mod n, and thus x to the power of ed is equivalent to x mod n. And that's really what we wanted to show. What we showed is that, in summary, raising to the power of d undoes our encryption. And that's kind of the beauty of public key encryption, is I can share with the world the number E, but in order to decrypt the message, I need to find D. And finding D involves finding this value P minus 1, Q minus 1. And if n is a really big number, then it might be really hard to find P minus 1, Q minus 1, because in order to find that, I need to factor n, and factoring is really hard. But what it shows me is that if I do know what P minus 1 and Q minus 1 are, if I do know how to factor n, then I can find this value D easily enough using our extended Euclid algorithm. And I can now use that to decrypt the messages that are sent to me. So I can share my encryption key with the whole world, and then only I know how to decrypt the message. It's a wonderful thing. Don't we love RSA encryption? It's very nice. So there you go. That's kind of why this certain central property is true.